Well, thank you for joining us, guys, for another ASCII webinar. My name is Clint Burtonshaw, and I am the Senior Operations Officer here at ASCII. And we have the third part of a series that we have been running with Lexion and Sean Gates regarding the Multi-Echelon Inventory Optimisation, or MEIO for short. You can see that Sean is the Managing Director of Lexion Solutions, and he has kindly given up his time again to go through the final part of this series, which also has a special treat in store, in that we have Astrid Tuan, who is currently in Melbourne at the moment, and she will be connecting onto the webinar as well to take you through a bit of a system simulation as well. So that's going to be quite a bit of a treat. I'd like to just put a little caveat in on this. Obviously, we are going to be running a system simulation over a webinar type structure. So if there are any technical issues, I'd like to apologise in advance. Needless to say, we are recording this webinar, so you will be able to go back and take a look later on, as well as the previous parts 1 and 2 of this series. They will be on our website under the resources section. At the moment, they're not there if you are looking for them, as they're being re-uploaded. This is an exclusive educational webinar series, and it's been provided by Lexion, and it's available to our ASCII members. So thank you again for tuning in. And without any further ado, I'd like to just give you a bit of a introduction as to what it is. It's the third and final part of this series, and we'll focus on the MEIO case studies. It will use the Lamasoft software to model MEIO changes in a complex supply chain. Great opportunity to see the MEIO methodology in practice, but also to ask questions. And towards the end there, we will be allowing you to ask questions. How we will probably do this is through the raise hand function. So please make sure that you are aware of the raise hand function. And make sure that you're actually connected to some kind of audio to speak, so be it a PC headset or you're connected via a phone connection. As always, however, if you do think of any questions post the webinar, or you are unable to actually communicate over the wire live, you can always email us, and we'll throw an email address up at the end of this. So let me hand over to Sean, who will do a few introductory slides. Sean, thank you for joining us today, and let me pass the controls over to you.
Okay, thanks, Clint. Can you hear me? Sorry, we're just getting the technology working. There we go. Okay, can you hear me now? Okay, I've just got a few slides to go through, so welcome on my behalf. I think those that have seen all 3 parts, you probably deserve a medal, but it's certainly been worthwhile, certainly from my perspective. I'm just going to go through a few slides. We're going to really recap some of the concepts from last time. They're important to understand or refresh your mind before Astra takes you through some of the software in terms of dealing with that. So just going to refresh some of what I talked about 6 weeks ago. MEIO, multi-echelon inventory optimization, different from traditional inventory optimization where you're dealing with individual islands. Here we're looking at the entire network. So there is a process flow. We have a fixed network, so we're starting with a network that we already have. There is obviously data cleansing and demand characterization. So we have to look at our demand to see whether it's fast moving, slow moving, intermittent, etc. We classify the demand, and that's important for our lead time demand distribution. So what does our demand look like during our lead time? Because that's really what we need to cater for in terms of our safety stock, which we then do our safety stock optimization using the multi-echelon inventory optimizer. And out of that really comes your inventory policy. It's where the rubber hits the road. That's where you've got your order points, your order up to levels, etc. So that's really where you're turning a lot of this work into execution, into planning. How does demand propagation work? You would have remembered from the last presentation, very simple structure: supply, warehouse, 2 facilities, 2 customers. Each customer has its own demand series, so a particular profile of demand sales that occur. The question is, well, what happens at the warehouse? So we need to propagate that demand from the customers up through the facilities into the warehouse. So our propagated demand at the warehouse can look quite different. You could imagine if you've got several thousand customers with a product that's very intermittent and very slow. Once you aggregate that, you can get a very nice manageable pattern of demand at the warehouse level. Effectively what I've just said. There's a whole lot of smarts we have around figuring out what the demand will look like. Demand mean, standard deviation. We look at non-zero demand mean and standard deviation, and interval demand interval mean, so the average intervals between demand. We propagate all that up to the warehouse, so that is really where our planning is going to occur. Examples of major demand classes. I actually didn't go through this slide last time, but just very briefly, it's fairly intuitive. You've got less variable and more variable demand. So less variable means it's perhaps more predictable, not intermittent, so it's nice and smooth. You're expecting sales to occur every month in a reasonable format. If it's intermittent, it might be slow, but there's not much variability. So we're selling much the same every now and then. More variable and erratic. We're having more variable sales, more up and down. It's more erratic. And then you get lumpy. The wonderful test of all demand classes is lumpy. So highly variable and very lumpy. So you might sell a few this month and then wait 6 months, you might sell 3,000. As I mentioned very briefly, importance of lead time demand distribution is we really need to look at what our demand is going to look like during that lead time, because that's really the period during which we've got to set our safety stocks. Talked about this last time. Your observed demand density, like the graph on the left, can be very different to a normal density, the bell curve that I think we're all very familiar with. So using a normal distribution to describe this observed demand density would be wrong. So we need to pick something like the gamma probability. It's a better fit for the demand during that lead time. It's going to give us much better results. Safety stock optimization. We talked at length in the last presentation about this, particularly service time. Just to refresh your memory, period of time between the order receipt and order dispatch, and we wanted a 0 service time at the customer-facing facility. Coverage is the net risk period that a site safety stock will cover. So as we go up through the network, we can work out the coverage at each of the nodes, and that will vary. And obviously we optimize our service times to minimize total safety stock holding costs across the supply chain in order to meet service levels. It uses coverage and lead time demand distribution to optimize those safety stock levels and placement along with the inventory policy recommendation. So the key takeouts from this, and Astrid will talk about this, is the service time and the coverage that will appear. So this is just a graph or a picture that builds supplier, manufacturer, 2DCs, multiple customers. The customers have different lead time demand distributions. They get propagated up through the DCs and into manufacturing, back to our single supplier. We can create a safety stock curve at each of those points. And then finally, we can formulate the problem using each safety stock curve and constraints, and then obviously solve for coverage and service time for each site. So once we've set the safety stock curve, we can pick a point on the curve which will give us a particular safety stock for a particular coverage, and then we can solve for each service time that we need at each site. Just preempting a few questions, my last slide before I hand over to Astrid. we need to use software. We went through a very simple example in session 2, but the real world is generally far from simple. We have a number of echelons, a number of products. So preempting some questions you might have, what about split sourcing? So I've got multiple suppliers going into the same node for the same item. Yep, we should be able to take that into account. Split mode, so that's transport mode. So we've got air, rail, road. Each of those will have significant differences about them because they're going to have different shipping quantities, different MOQs. They'll be different. So we need to take those into account. Do we need to look at components, intermediates, and finished goods simultaneously? Obviously, the system does that. Non-normal or smooth demand, we've talked about that. Multiple service definitions. You might be asking, well, we measure a service in a particular way, and we need to be able to try and replicate that at the customer level. So we've got 3 types of service definitions that we use. Type 1 is just really the probability of not stocking out during the replenishment cycle. Type 2 is a quantity fill rate. Type 3, what we call a ready rate, or percentage of time when we have stock on hand. Each of those has a different solution, and we'd use the one that most suits the business. So, yep. Quick and easy what-if scenario and setup analysis. Yep, that's fairly straightforward. Ability to run complex multi-branch and loop networks. Even I had to ask Astrid about this one. So if you've got a supplier that supplies location A, location A adds some value to that item, sends it to, location A then sends it to location B. Location B then adds some value to it and sends it then back to location A. In other words, it's done the loop. We need to be able to take account of that. So if you've got questions around, I've got a really complex network, this process, this problem solving should be able to help you. And obviously integration with network optimization. So we had a set network from the first slide, but you might want to say, can I do this and play with my network if I want to change where I've got my DCs, etc. So just preempting a few questions there that you may have in your mind at the end of this process. Obviously, it's quite powerful to be able to do these different things. Now, I'm going to hand over to Astrid. So hopefully in those few slides, it's twigged your memory if you were in there in session 2. And Astrid will take us through really the application of MEIO, and she will show some differences to IO. So we'll take the same problem and look at it from a traditional point of view, and then we'll look at it from the multi-echelon point of view, and then she'll extend that by looking some other options with MEIO. And then depending on how we go with time, we've certainly got some case studies to look at. So I'll hand over to Astrid. Thank you.
Great. Thank you, Clint, and thank you, Sean, and thanks everyone else to join me today. So I will go into Supply Chain Guru and show you multi-echelon inventory optimization in there. I'll first do a brief overview of the UI because many of you may not have seen it before, and then talk through a demo model, as Sean says, talking about the traditional way of only holding finished goods close to the customers, and then talking about what we can do if we look at it from a multi-echelon perspective. And time permitting, I'll talk you through 2 case studies at the end as well. So this is when we open up Supply Chain Guru. I have my recent projects that I can open. I can find help, go to our support website, for example, and several models down here to get me going. And one of them would be a safety stock optimization model. Going into Supply Chain Guru itself, you can see at the top this ribbon with different tabs, similar to the Microsoft Office suite of tools that most people would be familiar with. Under Home, can do admin sort of operations like saving, copying, uploading to the cloud if I want to share with my coworkers, or run multiple scenarios in parallel on the cloud. Under Tools, some visualization, so I'm showing a map here as well. And we have something called Visual Modeler that I might bring up at some point as well. some ways to quickly get data in and out via Excel. If I'm looking to put things on a map, geocoding, road distances, etc., different tools. And under model data, I can access my input tables, which I can also access from what we call the project navigator. So I have 3 models in here, and each of those models has a set of input and output tables associated with it. And these are the input tables for this model, which I can open from up here or from the project navigator. And then the different technologies within Supply Chain Guru each have their own tab for transportation optimization, simulation, and under optimization, I can run my network optimizations and my inventory optimization problems. So I can access outputs here, both in tabular and graph and chart format. So that's very brief about the user interface here. Then I'll go through my safety stock optimization demo model that I have here. This model is an Australian-based company that imports raw and packaging materials from overseas, has some manufacturing in, actually I'll just talk through it in here. So I have a packaging supplier in China, a raw material supplier in India that ships raw materials to Kuala Lumpur, where, and I'm bringing up the sites table and bill of materials table as well. So my raws here are turned into intermediates at this plant in Kuala Lumpur. The intermediates are then shipped to a plant in Perth, where I turn them into bulk goods, which is shipped to a plant in Melbourne, where I turn the bulks together with the packaging materials into finished goods, which are then distributed to 3 DCs, the green squares, if you can see it hopefully. And the distribution centers then ship it to the customers around the country. So what we'll look at in this model first is what does my inventory look like if I say I'm only holding safety stock for finished goods at my DCs, which are my customer-facing nodes, which would be the traditional way people may have thought of safety stock. And then as a next step, we'll look at what does it look like if I allow finished goods to be held at my filling plant, for example, or what happens if I allow holding of intermediates, bulks, raw materials further upstream. Will that overall lower my total safety stock cost within the system? And we can then start looking at some other scenarios as well, where we vary the service levels to see what cost increase will I see for what sort of improvement in service. And I also have a scenario around changing the variability in the lead times to see how that affects my safety stocks. So I'll talk through some more of the inputs, and then talk about the outputs and some visualization of that. And along the way, we'll hit on how the scenarios are set up and which ones I've run as well. So I opened the sites table as I was talking through this, just not looking at the customers, but all the different locations. And to visualize, we have the latitudes and longitudes on there. And then for the products, what we model within each model in terms of raw materials, finished goods, etc., really depends on the question we're trying to answer. So in this case, we have everything from raw, intermediate, bulk, and packaging through to finished goods. One important input here would be the product value that I'm on in this column. So that factors into my safety stock holding cost, which is based on product value, my inventory carrying cost percentage, which is set to 12% in this model, and the level of safety stock that I'm holding. And the bills of materials table tells us how much of each raw material goes into an intermediate. So for example, I take 4 units of raw 6 and 3 units of raw 7 to create 1 unit of intermediate 3, etc. And then I take my intermediates to create my bulk number 2. I have 3 intermediates with different quantities going in, and so on. to my finished goods as well, which each have a specific bulk and a specific packaging material to create my finished goods. Another important input into inventory optimization is the demand. So typically we capture this at the SKU level and also at the lowest level possible. So in this case, I have daily demand at my customer finished goods level, and I can see 65 units for finished good 2 at this customer on January 1st, 62 here, etc. And in total, if we go through, we can see that we have demand in here for all of 2016 at the customer level. What we do with that is, as Sean has explained, the first step of the safety stock optimization is to actually analyze the demand and classify it. So we calculate the needed statistics to come up with the demand class at the customer level, and then we propagate the demand upstream. And for that, we use the sourcing relationships that we set up in the sourcing policies table. So in here, we indicate for a customer which DC does the customer get its product from. And then for the DC, we can also see where the DC gets its product from, etc., etc. So we go further upstream. In this case, we have single sourcing across the board. But as mentioned before, we can also have multiple sources. If that were the practice in our network, we can set up multiple sources and indicate how much comes from each of the sources. Also in this table, you may see there's production time at the location where the product originates and source lead time where applicable. And this is where we can also factor in variability of it. So we can say it's normally distributed with a mean of 5 days and a standard deviation of 1 day. So this would be the probability density, looking at a graph for that production time, which is one of the lead times that we take into account when we optimize our safety stocks. So again, sourcing policies are used to propagate upstream. Transportation policies, this will tell us what are the source destination pairs and what are the modes that we use. In this case, we only have one mode in between all the source destination pairs, but as Sean was mentioning, we can have multiple modes like air, ocean, truck, etc., and have different characteristics for each. For example, different transportation times are also different what we call days between replenishment, which is really the replenishment frequency. So if we say 7 days, then once every week, 14 days, once every 2 weeks, etc. And like the production time and source lead time, we can put transport lead time in here, and we can put variability on top of that as well, which will be taken into account when we calculate the recommended safety stocks. One last input table I'll talk about before we talk a bit more about the outputs and the scenarios that were run. And that table is an important one. It's the inventory policies. So on here, we can indicate where we can hold safety stock and what the service requirement is. So this is at the location product level, as you can see here. And we have we are setting a service requirement here for our DCs. By default, it's 95%, but in the scenarios, I'm going to override that to 97, 98, and 99%. And if I do not set a service requirement at my further upstream location, so the non-customer facing ones, then this service level will actually be propagated as well as part of the demand propagation. So everything will be set up so that at the customer facing node, I can meet the service requirements that I'm requesting. We can put in constraints here as well. If we, for example, always keep a minimum level of safety stock, we can set that in this column. So regardless if I need that much to meet my service requirement or not. If I put a minimum in here, then the model will put that much safety stock there. I can also put in a maximum. Of course, if I'm then requiring a service level that is too high, that I cannot reach by not going beyond the maximum, then the models may come back saying that it's infeasible, and then we have some tools to diagnose that. But if it is possible to do so, to still meet the service requirement with the maximum, then maybe the model will put safety stock elsewhere to, in total, cover all the lead time that we need, but just distribute it differently. As Sean mentioned, service time is an important variable within the safety stock optimization. At the customer-facing nodes, this is by default 0, but we can override it if we want to by setting a minimum service time, for example. And for non-customer facing nodes, it's a decision variable, which can be between 0 and maximum lead time at that node. And again, if there are business rules that limit this service time, then we can set a min and max service time that the optimization needs to adhere to when we run it. Lastly, in this field stocking side, we can indicate if a location is actually a non-stocking location, so we don't hold safety stock there. Again, you may have to be a bit careful with this. If you're a customer-facing location, that in order to meet your service requirements, you pretty much always need to have at least a little bit of safety stock there. So if you set it to no, then you may not be able to meet your service requirement. And lastly, product value here. So we saw the product value field on the products table. That will be used globally at all the locations, unless I override it here, where I can say my finished good at the filling plant, the value is slightly lower than at my downstream DC, for example, because then I've transported it and it has appreciated in value, and then I can set varying product values by location. If that's the level of detail that I want to go into, that's possible. All right, so enough on the inputs for the moment. When we then run our safety stock optimization, what comes out on the output side, 2 tables to look at first will be the customer demand profile and also the facility demand profile. So this is where we calculate all the statistics that we might need, like the non-zero demand mean, standard deviation, demand mean, etc., the demand interval mean, and that all together leads to a classification, which is listed here. So for this customer and finished good number 3, the demand class is slow. We've determined that it's intermittent and low variable, so that puts it in the slow bucket. And I can look through this and you will see that most of my demand is slow and some of it is lumpy when we look at the customer. So just sorting for that, lumpy, and then the rest of it is slow. And then the next step that it would have taken is to propagate the demand upstream to the facilities. And again, we see at the location product level what this results in terms of a demand class, and it will also repeat all the statistics that it calculated and used for the classification, plus a few additional ones. And you see that my slow and lumpy demand downstream, when propagated upstream to the DCs and further to the plants, results in erratic demand, just one record that's lumpy, and the rest of it is actually smooth or normally distributed demand. And this is often what we see, that the demand classes at the customers can change when we put it all together and aggregate it upstream to the DCs and plants, etc. And it's not always that slow demand turns into smooth demand or erratic demand turns into non-erratic demand. It could also be the other way around, but oftentimes what we will see is that variability at the customers evens out to some extent, when we propagate it upstream, but it's all dependent on the network, of course. Then talking about the different scenarios before we go into looking at the safety stock outputs. As mentioned, we've run several scenarios, and the first one is to look at safety stock in the traditional ways, where we only put safety stock as finished goods at the DCs. And in this scenarios manager, I have set up 6 scenarios in total. And what these do is, when I run a scenario, it takes into account all the data that I have in my standard tables, except for the 1, or in this case 2 changes that specifically I make to it through my scenarios manager and these items. So one item changes my stock inside setting to no or to false, so that now I'm saying all the locations except for those that start with DC can now not hold safety stock. And this is how I make it so that only the DCs hold safety stock. And I'm also setting the service requirement to 97%. And then I have the multi-echelon inventory optimization here, where I do allow safety stock at the other locations, at the non-DCs as well. And again, I set my service requirement to 97%, 98, 99, which will look at the outputs. And then the last scenario here has a few more items in it. And I'm actually doubling the lead time variability on the transport time. So between my plant 2 and my filling plant, it was 5 days with a standard deviation of 2. But now I'm doubling the variability to 4 days. And similar for all the others, I have doubled the standard deviation, so the variability in the transport time, to see how that affects my safety stock. And I'll repeat this when we go through the outputs. So besides the customer and facility demand profile that we just looked at for the classifications, the table that we look at most will be the inventory policy summary table, where we see at the site product and also period level what is my recommended safety stock. And this is in terms of units, but it's also translated in terms of days of supply. And what is my holding cost associated with that, and the value of holding 33,000 units of this finished good. And if there are cycle stock and work in progress inputs, then we will report that here too. So in the first scenario, we set only hold for safety stock at the DC level, so that's finished goods. And that's what we see here. So we have sorted this by name, and the DCs are on top, and all the 5 finished goods. And we see their safety stock here. And none of the other locations hold any safety stock for any of the materials. And we can sum up what the total cost is, and that's 13.5 million in this case. Then I can switch to one of my other scenarios, and let's compare this with the multi-echelon inventory optimization, where I'm also requesting a 97% service level. But now, in this case, I'm also allowing safety stock to be held at non-DC locations, so at my filling plant and my further upstream plants too. And you will see that still I have safety stock at my DCs for each finished good, because I need to have some there to meet my service requirements to the customers. But now the bulks are being held at my filling plant as well, and my packaging materials, of course. And some intermediates are also held further upstream. You may remember the total safety stock cost in my first scenario was 13.5 million, and now it's reduced to 10.9 million by shifting some of my safety stock upstream. I can hold a lot less upstream, and also less of a more expensive product to hold. So in total, that reduces the safety stock cost quite a lot. And then let me give you an example here. For example, let's look at one of the finished goods. So what I've done here is just filter for the different scenarios for one site and one finished good. And starting with only holding safety stock at the DCs, we see that that's high as compared to the other scenarios. We hold 49,000 units of finished good 3, but when we allow it to also hold stock further upstream, we can lower this to 21.5 approximately. Then if we compare 97% target service level with 98%, we see that, of course, we need to increase our safety stock levels, and if we go to 99, even more. And the last one here, when we double our variability in the lead times, we see, and we still request a 97%, so comparing it back to the 97% one, we need to hold quite a bit more safety stock, 21.5 versus 30 points, about 200 units, which is even more than the safety stock needed to achieve a 99% service level. Lastly, in terms of cost, summarizing these outputs. So this is what I just clicked on, what we call a tabular report. It's pretty much Excel pivot tables within Supply Chain Guru. So for the different scenarios, I have summarized the safety stock, the total, and also the safety stock holding cost and value here in this table. And even though the total safety stock level is lower in the case where I hold it at the DC level, this is just because we add up the units. And there's multiple kgs of raws and intermediates that go into a finished good product, so that's why in the other scenarios the units look higher, but actually the total safety stock holding cost is lower because these are lower value products that we're holding further upstream, and we can reduce our safety stock holding cost in those scenarios. So if I compare the first one, only holding it at the DC level, that's 13.5 million. Now I can, for example, say even if I improve my service level to 99% and be smarter about where I put my safety stock, I increase my safety stock cost by just under 500,000, but I can increase my service level from 97% to 99%. Or if we look at it differently and compare these two, and I mentioned this before, if we place it better to reduce the overall safety stock holding cost, I can actually reduce my total costs by over $2.5 million here. And the variability one, where we doubled the standard deviations as compared to this one, is quite a lot more expensive. We need to increase our safety stock holding cost by close to, well, just over 5 million. So about, well, between 50 and 60% of the total. I'll show you some visual outputs as well. So we integrate with Tableau graphs and have some templates set up. If we open that up, then there are different templates that we pull the data from the model and that we use to fill up these templates. So the customer demand class summary, for example, you see that 97% of the demand was classified as slow, and then about 3% as lumpy. And at the facility level, when it's propagated up, we have 32% erratic, and close to 68% is classified as smooth. And another output or visualization that you can see here is all my locations, my DCs, my plants, and my suppliers here, and how much safety stock we hold of the different types of goods for the different scenarios. So it starts with the increased variability, lead time 1, 97, 98, 99, service level, and this is my safety stock only at DCs. So for this scenario that's farthest to the right, we do see there's no safety stock here at the filling plant, no safety stock here at plant 2, but a lot of safety stock at the DC, so in finished goods. At the filling plant, we hold some bulk, but also some packaging goods. And at plant 2, further upstream, I hold intermediates in all scenarios, but different amounts depending on the scenario that I'm running. So to summarize what we went through, we talked about the inputs into a safety stock optimization, how detailed demand is used to calculate the variability in the demand class. We use sourcing relationships to propagate it upstream, the different lead times and variability in it that we can set in the input side, and in the inventory policies table we can say what is the service requirement that we need to achieve. We talked about different scenarios, setting up different service levels, and also changing from looking from a traditional way, putting safety stock only at customer-facing locations in the finished goods, instead of, but then next we looked at the multi-echelon concept, where we can also allow it to hold stock further upstream, and looked at a variation in lead time, where we increase the variability. And on the output side, we looked at some individual examples and then the overall results by scenario here. And at the individual outputs here, one more thing here that I haven't mentioned before is if we scroll right, there's more outputs here, and as Sean mentioned, we arrive in the end at a recommended policy. For example, RQ, or in this case, the recommendations are SS, and the parameters to go with it. So in case of SS, this 49,000 is the reorder quantity, and my 56,000 is my order up to quantity whenever I fall below 49,000. So we can take that forward and put into the inventory management system if we want to operationalize these outputs. Lastly, I'll talk about two case studies, just one slide each to wrap this up. So this first example is for a large retail company, and the complications here are that there's a lot of SKUs that we are looking at in the network, and there's parent-child relationships for the SKUs in the DC structure. This company, before the project was done, they currently hold a fixed days of supply of each SKU, and that doesn't change based on what time of year we're looking at. And we don't look at something like demand classification. We don't look at it's slow or erratic, etc. And they were interested in understanding what sort of additional working capital would they need to put into the system in order to achieve better service levels. So their starting point was here, our safety stock quantity of around 150,000. So the red dot here would give them their current service level of 80%. So then different scenarios were run to optimize this, and what was found is to achieve the same service level, you can actually reduce the safety stock by about 25% in terms of when we talk about capital. And also, if we want to increase our service to about 90%, we can achieve that by only spending about 5% 20% more in terms of working capital. So by running different scenarios with aiming at different service levels, we can determine how much more working capital we need to put in to achieve a certain higher service level. So either we can maintain our current service level and spend less on inventory, or we can, by putting a little bit more in, actually go from 80% to 90% service level, which is a huge jump, of course. And with that, we can still free up some capital that is currently sitting in unnecessary safety stock, and therefore as well prevent some of the lost sales that were happening in the past, which amounts to about 75 million in this particular case. And this graph on the right-hand side summarizes the different classes that we're seeing in this case. So no normally distributed demand in this case, really. A lot extremely variable, some slow, lumpy, and erratic. And the last case study for today that we'll talk through briefly is a manufacturer of latches and fasteners. And the challenge here was that currently the team are reviewing manually the safety stock levels, and they want to put that into an SAP system for monthly planning cycle. So what was done on this project is run a lot of different scenarios, looking at the key drivers and running sensitivities and different assumptions on them to see what would really help in terms of lowering the safety stock required and or improving the service level. So we're starting here at this point 100% inventory and 100% service level. So this is our current inventory level with our current service level. If we go, sorry, I'm losing my mouse here. So if we go right, that means we keep the same inventory required, but we are improving our service level. And if we go down from number 1, it means we keep our current service level. That stays constant, but I'm actually lowering the inventory required. So for example, a scenario that's numbered 2 here, we can achieve the same service level if we can reduce our lead time by about 85%, and then we only need 80% of our current inventory. If we also reduce lot sizes and 85%, well, the lead time is reduced to 85% of current, then we can still achieve the same service level, but with a lot less inventory, between 60 and 65%. So say 62% of our current levels. Then if we go to the right, just optimizing and looking at where do we place it and how much do we hold, we can achieve a better service level. So talking about number 4, better service level with less inventory. And if we improve upon that further, we say we can reduce the lead time by 15% to 85% of current. We can still achieve that very good service level with even less inventory. So this really gave the company a good overview of which levers to pull and what the impact would be both on the service level and how much inventory they would need to hold for that. So the final conclusion was can at least save 15% by postponing production and taking risk pooling into account. So really the effect of the multi-echelon rather than looking at single echelon inventory optimization. So I think I'll stop there. Want to thank you all very much for taking the time to follow along with this. I think give it back to Clint and see if there's any questions.
All right, thank you, Astrid, for taking us through that, and once again, thank you to Sean for the opening up the presentation. All right, so what we'll do here, guys, is we do have a little bit of time for some questions. I'm just going to also unmute Sean. Okay, so what we'll do is if you do have a question, actually, maybe I will mute Sean so there's no echo from me. Okay. If you have a question, if you could use the raise hand option on your control panel there, or alternatively, feel free to type your question in and we can ask that out anonymously. It's not a problem. I'll give everyone a moment to either ask a question, raise hand, or whatever the case may be. Otherwise, what we will do is if there are no questions, we will close off the session for this afternoon. And as always, you can email us at events@ascii.org.au and we can get those questions through to Sean and Astrid and they can come back to you with a response. All right, not seeing any hands going up.
Everyone knows what's going on.
Looks like it. Looks like it. All right, guys. Well, given there are no questions, I will close off the session. Thank you so much for joining us this afternoon. Keep an eye out on our events calendar as we have more webinars coming up in future. And if there is anyone who is interested in finding out about the new CPIM reconfiguration, I am hosting an information webinar next Tuesday at around the same time to talk about the changes to the APIC CPIM reconfiguration. So please feel free to register and find out a little more. Otherwise, thank you very much and enjoy the rest of the afternoon. Bye for now.